Well, let's take a look at some more questions. Hopefully I can get a couple videos out today. It's Tuesday afternoon. Hope you're working hard on the assignment, and hopefully I can get a few more from the later sections done to help guide you through the odd-numbered problems that you're working on. I just wanted to mention something that I looked up in your Chang textbook. I talked about the use of the word standard, and there was a little lack of clarity on what version of standard was used in some of the problems. I noticed that on page 4 of our textbook, it stated that a pressure of 1 atmosphere is used to define normal melting points and normal boiling points. A pressure of 1 bar is used to define standard states of substances. So for example, if you want to know what's the standard state of carbon, you say it's graphite. The conditions under which you make that statement is 1 bar of pressure. Not exactly sure why. 1 bar is a little bit different than an atmosphere. If I recall, 1 bar is 100,000 pascals, whereas 1 atmosphere is 101,325 pascals. So it's a slight difference. On page 11 of this Chang text, STP is mentioned, standard temperature and pressure. Standard temperature and pressure states that you're assuming 1 atmosphere pressure and a temperature of 273.15 K, which is exactly 0 degrees Celsius. You might notice when I do some of these problems, I only use 273 Kelvin in conversions. That's because the value that I'm given doesn't have any places after the decimal point in Celsius. So you can get away with that small error. Let's take a look at a couple of the questions. There, here I have a mixture of nitrogen and hydrogen that in total weigh 3.5 grams. The volume is given at 7.46 liters, the temperature is 300 K, and the pressure is 1 atmosphere. What's the mass percent of each of the contributors to this mixture? Well, there's a couple of things that I think I'm going to need, and that is, given this information, it seems clear to me that I'm going to want to find out how many moles of gas I have and then use information to derive the mass of each. So there's two things that we know. We know that the mass of the N2 plus the mass of the H2 is equal to 3.50 grams. That's going to be useful for us to make a substitution in a minute. In terms of the moles, we know that PV over RT is going to give us the total number of moles of gas. So if I plug in the given information, I have 1 atmosphere pressure, a volume of 7.46 liters. They're making it easy on us. We don't have to do any conversions. R is 0.08206, and the temperature is 300 K. I get a value of 0.303 moles of gas total. Of course, the total moles of gas is going to be equal to the sum of the moles of N2 plus the moles of H2. Hopefully you can see where we're going with this, because the moles of N2 is going to be whatever the mass of the nitrogen is over its molar mass of 28.02 grams per mole. The moles of hydrogen is going to be whatever the mass of hydrogen is over its molar mass, 2.016 grams per mole. Right now we have a bit of a problem because we have a single equation with 2 unknowns. But you might recall we did that a little bit earlier. We can rearrange that to allow us to make a substitution. In other words, if I say 3.50 grams minus the mass of, let me pick hydrogen, I could make a substitution for the mass of nitrogen. So that's exactly what I'm going to do. If I substitute in that term, I end up getting a single equation with only one unknown. 0.303 moles is equal to 3.50 grams minus the mass of H2 divided by 28.02 plus the mass of H2 over 2.016 grams. I'll let you solve for the unknown, but what we end up getting here is a mass of H2 is 0.387 grams, and a mass of, that's actually the mass of N2. Let me fix that up. That's the mass of N2, and the mass of H2 turns out to be 3.113 grams. All right. You could use those to figure out a percentage, which is what the question was asked. If I take the next one, I wanted to just make a casual reference that there are some questions that I just don't like. I don't really care for this one because it has you make assumptions that are going to be really difficult to do. Take a look at this. They're asking you to do a calculation that tries to figure out how long a person would be safe if locked in a sealed room of this size. It's a bit of a creepy question, I admit. It makes assumptions such as the size of a breath. An answer that I found assumes about a half a liter, and that you take like 12 breaths per minute. Another assumption is that you have 20% oxygen in the room, and that there's a 1-to-1 ratio between converting oxygen into CO2. The bottom line is that it was a bit surprising to me, using their assumptions, that a person wouldn't suffer from CO2 poisoning for 13 days, which seems pretty long, but it's nothing that certainly would be any fun at all. So I just wanted to mention that if you come across a question and you just think it takes too much to assume, you could pretty much skip it. That's not anything that we would really need to test you on an exam or something like that. But I do have one more that I want to do in this video. 2.28 is another problem that involves a mixture. I think we did this one in class, but I'll go over it again. This is a case where you are going to use the fact that the partial pressure of individual gases add up to the total pressure. In this example, we've got a mixture of helium and neon, but the fact that it's collected over water reminds you you're going to need to account for whatever the vapor pressure of water is at that temperature. So we're told here that at 28 degrees Celsius, the vapor pressure of water is 28.3 millimeters of mercury if that sample's saturated with water, 100% relative humidity. And we're also told that the partial pressure of helium is 368. So this one's pretty straightforward. We know what the total pressure is 745 millimeters of mercury. The partial pressure of the helium, didn't really want to do that. The partial pressure of the helium is 368. The partial pressure of the neon is the number that we're after, and we were given the partial pressure of water. I'm just going to round it off to the whole number of 28 millimeters of mercury. If I solve for the partial pressure of neon, I get a value of, drum roll please, I get 349 millimeters of mercury. And I think that'll be it for this session. Take a look for some other videos a little bit later. Thanks. This is another problem that collects a gas over water. In this case, we're going to do a little bit of stoichiometry and try to figure out how much of the solid sodium generated this much hydrogen. All right? So let's take a look at the variables that I was given. We were given temperature, volume, and pressure. That's a big flashing red sign that we're probably going to use the ideal gas law. Keeping in mind that this sample of hydrogen was collected over water, so we're going to need to subtract the partial pressure due to water in order to use the ideal gas law correctly. So if the total pressure is given as 1 atm, and the partial pressure of water at 25 degrees is given as 0.0313 atm, The pressure that I want to use in the ideal gas law is 0.9687 atm. An extra sig fig than normal, but that's okay to keep an extra as we move along. So I'm going to isolate for moles of hydrogen is what I'm after. So I'm going to take the pressure and the volume of the hydrogen over the gas constant and the temperature. The pressure of the hydrogen is 0.9687 atm. The volume was given to me in milliliters, so I'll just do a little transfer of the volume right there to liters. The gas constant we should know very well by now, and the 25 degrees Celsius needs to be converted to Kelvin, 298 Kelvin. The moles of hydrogen churning through this ends up being 0.00974, stake there, 0.974 moles. And as I mentioned a little earlier, we have to be mindful of stoichiometry. So there's a 2-to-1 ratio between the sodium and the hydrogen. So I'm going to place 2 moles of sodium on top, 1 mole of hydrogen down here, and I get 0.0, lost my place, 0.0195 moles of sodium, and using a molar mass of 22.9 grams per mole of sodium, that means I need about 0.45 grams of sodium to generate this much hydrogen.